Hi everyone, I'm going to talk about distributed algorithms for fractional coloring. And this is joint work with Nicolas Bousquet and François Piron. So I'm going to explain first what fractional coloring is and why it's interesting in the context of distributed algorithms. So say you have some network, 5 nodes here, and each round nodes are active. Some nodes are active and perform some action. And what you want to avoid is that 2 nodes that are adjacent are active during the same rounds. And there might be many reasons for that. Maybe if 2 nodes talk at the same time, there will be some interferences if they're adjacent. Or you might have some symmetry problem if 2 adjacent nodes perform, maybe they might perform the same action at the same time, and you don't want that. So in any case, you want that each round, the number of vertices that are active is an independent set. Okay, so what you can do is find a proper 3 coloring of the graph with colors 1, 2, 3, and say that at round 1, the 2 vertices color 1 are active. Then at round 2, the 2 vertices color 2 are active, and at round 3, the vertex color 3 is active. And you repeat this cycle again, 1, 2, 3, 1, 2, 3, 1, 2, 3. So if you do that during 3 T rounds, each vertex is active during exactly T rounds, so 1/3, which is 33% of the time. And you'd like to understand if you can't do better than that. So can you find a different scheduling such that vertices, they're active a larger fraction of the time? And actually you can improve on this 1/3 bound by using this following ID. Instead of assigning a single color to each vertex, you assign them 2 colors, and 2 colors among colors 1, 2, 3, 4, 5. So here's you can do. So each vertex has 2 colors. And again, you can check that each color is an independent set, which is the same thing as saying that 2 adjacent vertices, they have disjoint sets of colors. And now you can do the same thing. Vertices colored 1 are active at round 1, then vertices colored 2 are active at round 2, and you cycle between 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So here during 5 T rounds, each vertex is active 2 T rounds because it has 2 colors. So each vertex is active 2/5, which is 40% of the time. And it's better than 33%. And you can ask yourself, well, is it best possible? Can you improve on this again? And no, you can't improve on that. The reason is that the largest independent set has size 2, and there are 5 nodes, so you'll never be able to beat 2/5. So this is best possible. And so maximizing this fraction 2/5, the same as minimizing the inverse 5/2. And so we want to maximize 2/5, but somehow in all this talk, I'll rather talk about minimizing 5/2, but this is completely equivalent. Okay, and so fractional coloring is exactly this, maximizing 2/5 here or minimizing 5/2. So this is why it's interesting in the context of distributed algorithm. It's really a way to find efficient scheduling protocols for in the distributed setting. Okay, so let me now give a precise definition of fractional coloring. So for integers p and q, you say that the pq coloring, it's a coloring of the vertices of a graph where each vertex has q colors out of p general colors. So colors are 1, 2, 3 up to p, and each vertex takes q colors, and you want each color class to be an independent set. And again, this is the same as saying that 2 adjacent nodes, they have disjoint sets of q colors. And the fractional chromatic number, which is denoted by KF, it's the infimum of all these fractions p/q, such that G has a pq coloring. And you can prove that it's actually a minimum. gets attained for some fraction p over q. Okay, so you can check that a p1 coloring is exactly the classical p coloring. So in particular, this shows that this fractional chromatic number is always at most the chromatic number. And also a simple counting argument tells you that it's always at least the clique number of G, the maximum number of pairwise adjacent vertices. Okay, so it's coined between the clique number and the chromatic number. And it turns out sometimes it can be very close to the clique number, sometimes very close to the chromatic number. There's no, I mean, there are many possible cases. And one interesting example where you can see that it can be very, very much smaller than the chromatic number is the example of Knesegraphs. So the Knesegraph K and K, it's a graph whose vertices are the K element subsets of 1 up to n, and 2 vertices are adjacent if the corresponding K element subsets are disjoint. It's very easy to see that the fractional chromatic number is at most n over k because the names of the vertices are exactly their colors. But you can put it at least n over k. It's a classical result in extremal set theory. So the fractional chromatic number is exactly n over k. But the chromatic number, on the other hand, is much larger than that. It's n minus 2k plus 2. And this is non-trivial. It was a conjecture of Kneser that it's at least this value. Proving that it's at most this value is quite easy, but at least it's difficult. And this was proved by Lovas in the 70s. So in this example, so let me just make a small example. This is K52, also known as the Peterson graph. And so I gave here a 3 coloring, okay? So here fractional chromatic number is 5 over 2 and chromatic number is 3. All right. So assume you'd like to find a fractional chromatic number in a distributed algorithm. With a distributed algorithm, what should be the output of your algorithm? So in a classical coloring algorithm, you output just 1 color, but here you must output q colors, okay? Assuming that the fractional chromatic number is p over q, it's a pq coloring, you need to put q colors, and all colors are integers from 1 to p. So the output size is q log p. But the problem is that p and q, they can be very large, much larger than this fractional chromatic number that you have. There are examples where the smallest p and q, such that the fractional chromatic number is equal to p and q, they are unbounded by a function of the fractional chromatic number. Okay. So this is a problem. And even if you don't bound p and q as a function of the fractional chromatic number, but the number of vertices, there are examples where p and q have to be exponential in the number of vertices. And it's a bit annoying. So usually when you consider locally checkable labelings, which are labelings that you can check locally by only looking at the ball of constant radius around you, what you assume is that the output of each vertex is bounded. Here, we might be quite far from that. But if you don't worry too much about the output size and allow anything, then you can prove some fairly amazing results. So this was proved 6 years ago. So you know that any graph of maximum degree delta has a delta plus 1 coloring, and you can always find that pretty efficiently in the local model in log star n rounds. So what was proved here is that if instead of coloring, you would just want a PQ coloring, and you want this fraction P over Q to be bounded, then you can do a little bit more than delta plus 1, just any function, any constant times delta plus 1. The constants would be larger than 1. And you can, the improvement is that you can do that in a single round, like just 1 round communication. So this is much better than log star n. And yeah, this is quite amazing. But of course, the P over Q is very large. Okay, so yeah, it's quite magical, but somehow what worries me the most is not so much the fact that P over Q can be very large. It's rather the fact that you don't really beat classical coloring so much. So the improvement is mainly on the number of rounds, but somehow if you really want to improve scheduling, what you want is to improve the number of colors. And here it's a bit less useful than just delta plus one coloring. So in this talk, at least, the goal will really be to find PQ colorings where this P over Q would be better than the chromatic number or bounds on the chromatic number that you would compute with a distributed algorithm. Okay, so we want to improve on this P over Q while keeping Q reasonably small and having a reasonably efficient algorithm. Okay, this is our ideal goal. But there's another motivation behind this work, which comes from complexity gaps. So all the results that I'm mentioning here are on the local model, where the network is modeled as a graph, and nodes can communicate with their neighbors in synchronous rounds, and there are no failure. Messages can have any size, and nodes have distinct names in the deterministic setting, and they have infinite computational power. So in this model, as I mentioned, you can find delta plus one colorings for graphs of maximum degree delta in log star n rounds. And I'm always assuming that delta is a constant in this talk. And what's interesting is that if you don't have a complete graph on delta plus one vertices in your graph, then you can do better than delta plus one. You can do delta colors. This is known as Brooke theorem. And in the distributed setting, what's really amazing is that suddenly, if you go from delta plus one to delta, now you need log n rounds for randomized algorithm and log n for the deterministic. So there's a huge complexity gap between the two problems, whereas you only just remove one color. It's a bit amazing. And you have similar gaps in trees and grids. Okay. In both cases, you go from needing at least order of n rounds for the few colors, and being able to do that with log n or log star n rounds with one more color. Okay, so there's a gap between 2 and 3 for trees and 3 and 4 for grids. So if colors are integers, there's nothing more you can say. But now if you have a rational number of colors, then you can try to see where the complexity threshold is. So is it, for instance, between delta and delta plus one, is it true that as soon as you have P over Q, which is smaller than delta plus one, you can go faster? Or where is the threshold? Is it closer to delta or closer to delta plus one? You can do that if you have a number of colors which is rational. Again, so here are our results. So we proved that basically if P over Q is equal to delta, it's as hard as delta coloring. So there's no, looking at fractional things doesn't make anything easier. But now with PQ coloring, whenever P over Q is at most delta plus epsilon for any fixed epsilon, you can find a PQ coloring in log star n rounds. Okay, so the threshold actually is as close as you want from delta. Actually, the threshold is delta. And we have similar results for trees and grids. So trees, P over Q equals 2. This is hard, but 2 plus epsilon, it's easy. And the same for grids. 2 is hard and 2 plus epsilon is easy. But there's a small, it's a bit strange here, the result for grid, because remember that when you had an integral number of colors for classical colorings, 3 was hard and 4 was easy. But if you go now in the fractional world, the answer for what the threshold is 2. It lies outside of the interval between 3 and 4. So something strange happens here. Okay, so and all these results, P and Q are reasonable. They would depend on epsilon, of course. And let me now explain the ideas behind these two results about the maximum degree. Okay, so first I'm going to explain you how to prove that we can, for any P in Q, for any fixed Q, we can find a PQ coloring such that P in Q is at most delta plus epsilon. And for this, it will be enough to take Q fix any Q and takes P equals Q delta plus 1. So Q delta plus 1 divided by Q is delta plus 1 over Q, so it's delta plus epsilon for any epsilon. So we want to find a Q delta plus 1 Q coloring for any fixed Q. And the way we do that, so Q is fixed, and we're going to take a maximal family of vertex disjoint induced paths of length 2Q plus 1. So they're vertex disjoint, and they're maximal in the sense that you cannot add one more pass on 2Q plus 1 vertices that would be disjoint from that. And in particular, it means that in the remainder of the graph, if you remove all these paths, all components, they have small diameter. Okay, because if some component had large diameter, you would be able to take a shortest path between 2 points that are far apart, and it would be an induced path on 2Q plus 1 vertices, and you could add it to the family. So all remaining components, they have bounded diameter, so you can color them easily. We are in the local model, so we are in a graph that has no K delta plus 1, and we have maximum degree delta, so we can find a Q delta Q coloring. So it's also a Q delta plus 1 Q coloring. And now the goal is to extend this coloring to the path. But what's a bit annoying is that you might have some edges between these paths. So what you're going to do is you are going to group these paths such that in each group you'd have no edges between the paths. And you can do that because you can consider some graph which is obtained by contracting all the paths. And this graph would have bounded degree because Q is bounded, delta is bounded. So you can color this graph in log star and round. And the coloring would give you exactly this grouping into a constant number of colors. And once you had made these groups, you can extend the coloring from the right to the left, group by group. First group, second group, and third group. And the reason why you can extend the coloring of the whole thing to a group is that you can extend the coloring to each of the paths in parallel because you have no edges between these paths. And the reason why you can extend the coloring to everything, from everything to a path, it's a least coloring result from graph theory. It's actually a non-trivial lemma. Okay, so all I have been using there was maximal independent set and coloring in graphs of maximum degree delta. So everything can be done in log star and round. Okay, so this was the proof. And why, now let me explain why the lower bound. So why Q delta Q coloring is as hard as delta coloring. And for this, we're going to make a reduction from the Sinclair's orientation problem in delta regular graphs. Sinclair's orientation, you have a graph and you have to orient the edges such that each vertex has out degree at least 1. And it's hard. It's at least log n round randomized and log n rounds deterministic. So you give me your delta regular graph and I replace every vertex by a clique on delta vertices. Like this, delta is 4. And let's assume I know how to find a Q delta Q coloring of this graph. So in a clique, so we have Q delta colors and each vertex has Q colors. So in a clique of size delta, all the colors have to be in the clique, okay? Because you have Q delta colors, Q vertices, delta vertices, and Q colors in each vertex. And in particular, the color 1 have to be there in each of these cliques. And what's important is that the unique vertex that contains color 1 in the clique, that it's not adjacent to another vertex of another clique that has 1, because it's a PQ coloring. So what you can do now is each vertex of the original graph looks at its vertex that has color 1 and orient the edge in this direction. So this vertex has color 1, so we're going to orient the edge from the bottom to the top, and here from left to right. Okay, so yeah, this is the orientation. And now this has to be a singlet orientation because each clique contains 1, so we're going to orient at least one edge out of the clique. And no, there won't be any conflict, because if 2 vertices had oriented the edge in the same direction, 2 adjacent vertices would have had color 1. It's not possible. Okay, so yeah, here's the proof. And I'm going to conclude now with a couple of remarks and open questions. So as we have seen, so our goal was really to find efficient algorithms for PQ coloring with such that P over Q is much better than the chromatic number when this is possible. For specific graph classes where you can have this margin between the two. And I said that sometimes you have to take P and Q quite large. And the reason for that is that a PQ coloring is also a P coloring. So if you have a PQ coloring, each vertex has Q colors, but each vertex can just take 1 color out of its Q colors arbitrarily. And what you have is a coloring, is a P coloring. So it means that whenever you have a PQ coloring, P is at least the chromatic number. So if chi is very large, say linear in N, and P over Q is a constant, this means that both P and Q would be linear in N. You can't avoid that whenever you have a PQ coloring. So yeah, sometimes you have to take P and Q quite large if you want to have this gain in the scheduling, but I don't think it's so bad. If you have a huge number of rounds of communication over the long run, what's really important is this ratio P over Q, not so much the fact that P and Q are large, I think. So one example of the result that I have in mind is this result that we obtained recently with Sébastien Judiot and Arnaud de Mesme. So we obtained a constant time algorithm in the local model to color unit disk graphs. So unit disk graphs are intersections of unit disk graphs in the plane. They model wireless communication networks. And there was a classical 3 approximation algorithm for the chromatic number. So coloring with at most 3 times sky colors. And we can make a very simple PQ coloring with P over Q divided, that would be at most 2.1 omega. Omega is the clique number, it's always at most the chromatic number. So it's always at most 2.1 times chi. So it's almost 30% improvement over this 3 chi classical bound. So yeah, and Q is small and the algorithm is very simple. So this is really what I had in mind. So can we find algorithms where this P over Q is really better than chi, and without making horrible things with okay, so final question. We saw these examples of graphs, Kneser graphs, that have very small fractional chromatic number, but very large chromatic number. So now if I give you some specific graph K and K, I give you N in the K, and I tell you, can you color this graph, this family of graphs efficiently? The local model of computation, say, find some very small P and Q with very small ratio P over Q, such that you can color these graphs. Can you do that efficiently in the local model? This will somehow tell you how easy or how hard fractional coloring is in the local model compared to classical coloring, where for instances where the two are really completely different. And yeah, thank you very much for your attention.